Okay, so before we get started today, a um, important announcement. There is no class next week because I'll be out of town, so both days no class. But I have lectures posted, that is posted for both days, so make sure you watch them. And this was announcing the CS140. The quizzes are also, you're responsible for them as you normally would be. So if you have not yet ever done one of the lectures, if you go to lecture notes, actually every day I am posting lectures. Generally I'm recording, but, whoops, sorry, that was not what I wanted to select. So if you look at next week, you see we're going to be moving into the design of databases, and next week is looking at entity relationship modeling. So on Tuesday, I'll be posting 2 lectures here. They're not posted right now, but I will be posting them, and they are lectures from a previous semester where I lecture just like I do now, and using the tablet to do the kind of whiteboard stuff. So it's just like having me there, except you can't interactively ask questions. I'll still have access to Piazza, so if you have questions, feel free to post them on Piazza. The first day is going over the concepts of entity relationship modeling, and then the second day is going over a case study. So when you see this investment firm design case, that's the second day. And what I found is if I just go over the concepts of entity relationship modeling and then turn you loose on the homework assignment, it doesn't work out well. Students really don't seem to get it. So that's why I spend a whole day going over a actual case study so that you can see how you need to be doing it for the homework assignment. And that is homework 4, so still a bit in the future, but just letting you know, you definitely are going to want to be looking at the lectures. So while there's no lectures posted right now, there will be 2 lectures posted, so you will be responsible for them. Remember, it's often good to increase the speed to about 1.5 times. Not only does it go more quickly, but actually studies have shown that you often learn better because our minds, turns out, process information more quickly than we speak. So questions about that? Remember, you still are responsible for the quizzes as well. They will both be due 2 days after class or after that normally scheduled lecture. So the Tuesday one will be due Thursday at 12:30 as is normal. The Thursday one will be due Saturday at 12:30 as is normal. And also remember, while there was not a quiz over the relational algebra and calculus on Tuesday, there is one today. So make sure that you do that one as well after class today. Okay, so questions? In that case, just a quick review. So we are, this week, covering the theoretical foundations for the direct manipulation language for relational databases, and that's often also called the query language for the database. And on Tuesday, we were looking at the relational algebra. Today, we're going to finish up the relational algebra and move into the relational calculus. If you remember, the relational calculus is what is actually the foundation for the direct manipulation language for the relational model. And the relational algebra is something that was introduced later. It was more of a high-level procedural language, whereas the relational calculus is a high-level declarative language, meaning you don't actually tell the query optimizer how to perform the query. And this term relationally complete means that if you devise a query language for a relational database system. We say it's relationally complete if every query that can be formed in the relational calculus can also be formed in your query language. So the relational algebra is relationally complete because every query that can be formed in the relational calculus can be also formed in the relational algebra. In other words, the relational calculus is reducible to the relational algebra. Okay, so last time we went over the basic operations in the relational algebra. As a quick review, it's select, project, Cartesian product, set union, and set difference. And then there's three ancillary operations that are syntactic sugar that are not part of that base set, which is join, set intersection, and set division. Last time we covered 7 of those 8 operations. The only operation we did not cover was set division, which is the one that we are going to cover today before we move on to the relational calculus. So, okay. So again, set division is a query where you're essentially looking for the, I'll say, people who have done everything of something. So in the example you see up here, we are looking for all guests who have stayed in all rooms in the Grosvenor Hotel. And there's 3 rooms in the Grosvenor Hotel. So we're looking for the guests who've stayed in all rooms in the Grosvenor Hotel. And if you look over here, guest number 20 has stayed in room 100 and room 300, but guest 20 has not stayed in room 200, so guest 20 will not be in the result. Guest 30 has stayed in room 200, 300, and 100, so has stayed in all 3 rooms, and therefore will show up in the result. And guest 10 has only stayed in room 100, and therefore will not show up in the result. So again, we're looking for people who've done everything of something. And another way to think of set division is as a join, except that now, instead of being able to appear in the result if you match any row in the right side relation, now you show up only if you match every row in the right side relation. So it's like just a more stringent version of a join, okay? So that's another way to think of it, is you have to match every row in the other relation. So guest 30, in some sense, matches every row in this room number relation, because for every tuple in the room number relation, there is a corresponding tuple for room number, or for guest number 30 in the booking relation. Okay, it's 2 questions. I'll take yours first.
So division is essentially just the proper subset of a set?
Proper subset of a set. You're going to end up with, well, not exactly, because you could end up with every, I mean, if there was 9 tuples in here for 10, 20, and 30, actually 10, 20, and 30 would all end up in that result. So not exactly. It depends how you define proper subset, right? There's almost always going to be fewer tuples in the result than in the original relation. But if you then think of doing a select distinct, which is what essentially set division is doing, then it's not necessarily a proper subset. Okay. Yes? No, it's okay. So the question was, is set division always just on one column? Because that's what we've been showing. In reality, this right side relation could have an arbitrary number of columns, but in practice, usually it's going to be a single column. I have to admit I could probably try to come up with a set division operation. Okay, here would be one. Let's say I was specifically interested in guests who had, I come up with a certain set of dates, like say Christmas to January, Christmas to January. Maybe I'm interested in the set of all guests who have stayed with us every Christmas and New Year's from 1965. I'm sorry, I was thinking of my birthday. From 2010 to 2018. Then I might have a date from and a date to. Okay, so then I would have a 2-column divisor. So yeah, it can be 2 columns, but usually it's going to be a single column. Other questions? Okay, so I gave, so the preconditions for set division is that the set S, which is the divisor, has to be a proper subset. The attributes in S have to be a proper subset of the attributes in R. So if R has the attributes A, then S, the attributes in S, the divisor, must be a proper subset. So that is a condition. And then in the result is tuples from R. It's like a semijoin, okay? So we're only interested in the result in tuples from the dividend, which is R. And specifically, we're only interested in the attributes that are in R, but not S. So it's actually the attributes in A minus B that we are interested in. So I would argue that while the book defines it as B as a proper subset of A, it really should be that B is not a proper subset. I would argue B would have to be a proper subset of A because you want at least one attribute to be in your result. Okay. And then, as I said, it's a more severe form of a semijoin because every row must match the row in the divisor. And I have to admit, when I first did these slides, I was trying to get my head around set division. So I will go over these slides because when I was trying to learn set division, this is how I thought about it. And now I have this more, I guess, better understanding of what it really is as being a severe form of a semijoin. But when I was first trying to learn, I was thinking, okay, how do I calculate the result? Well, the first thing you do is you cross out, which I did in red, all the tuples in R that don't match S. So here, Ralph has attributes, values A for Y and 1 for Z. So that just doesn't match at all. So it can't possibly be in the result. So then what we're left with is just the tuples in R where the attributes for B, which are also the attributes in S, exactly match. And then you just start going through it line by line. So Ralph is A6. So now you try to find all the other entries for Ralph and make sure that they completely cover all the rows in S. And then you repeat that for Mary. And then you see that Fran is not going to meet our criteria because Fran only has one of the 2 tuples in S. Okay, so that was a concrete way of doing it. If that helps you when you're computing set division, that's great. Now I find it a lot easier to just kind of, I guess what you would do is kind of a group by operation. You would try to group all the tuples for the attributes in in C. So basically you'd want to do a group by all the attributes in C. So you got all the tuples organized together, and then you'd make sure that each set matched all the tuples in the divisor. Questions about that? Okay, I realize set division is the hardest one to get your mind around. So next, remember it's a courtesy operation, syntactic sugar. It can actually be derived from the other operations in the relational algebra. So the way we derive it from the other operations is in 3 steps. The first step is to simply do a projection on R in the attributes in C. Remember, C is the set of attributes in R that are not in S. So in this case, when we look at R and S, we see that the set C is equal to X because R shares the column Y with S. So we're going to first do a projection on R on the attribute X. So we get this relation right here with the tuple with the rows A, B, and C. So that's step 1. Then step 2 is we take the cross product of all the tuples in T1 with the tuples in S. Okay, so that gives us this relation right here. So what that means is if these tuples in R matched every row in S, this is what that relation in R would look like. Okay? And then the third step is still part of the second step, is to subtract from this relation right here, R. So now this relation, subtract this relation R from it. Okay? And when we do that, we get whatever is the remainder. Okay? And I'm going to have trouble writing on this slide, but I'll do my best. So let's opt for blue. Okay, and so right here you see the comment, remove from R the multi-rows that match S. So what we really want is the remainder. This is giving us the remainder. Okay, so when we subtract this R from this T crossed by S, you can see that what is going to be left is only C2. The only thing you're going to have is, just a second, you're only going to have C2. So when you do that, all you're going to be left with is C2. Okay, that's the only thing in this relation that is not in this relation. So this is the remainder. Right here, C2 is the remainder. And now in step 3, so now we take the projection. So the third thing we do is we project that and we get C. So here the result of doing the subtraction, right here, what we've come up with is the rows in R. So this now is the rows in R that do not match everything in S. Okay, so these are the rows in R that do not match everything in S. And I'm sorry that I'm slopping over, but so what we're getting is if you have a set that matches everything in S, then it will be completely removed from this relation right here. And so all we're left with is stuff that does not completely match S. And so the final thing we do is we subtract T2 from T1. So what we're saying is from the original tuples in R, subtract out those that do not match all the rows in S, and we're left with A and B. Okay? I'm not claiming this is intuitive. As I said, it wasn't until I taught it for like the third or fourth time that I really wrapped my head around it, and you're forced to do it just once. So you may have to study that a bit. But that's the formal derivation of set division in terms of the basic operations in the relational algebra. Okay? And actually, when we get to the relational calculus, I'll end up showing you how you can kind of do that in how you can specify set division in SQL. But before we do that, you now can just take a quick brain break. So in the relational algebra, there is some, again, notation for aggregate operations, which is just crazy. So they just choose these Greek letters, and I have no idea. I guess the P looks like print. So for aggregate operations, you use this tau, T, the strange T, Greek letter, and you list your aggregate operations down here. So the AL stands for aggregate list, and it could be min, max, sum, average, or count. This is the relation you're doing the aggregated operations on, and these are the column names in the result. So for example, if I am counting the number of properties whose rent is 350, this is how it would look. Here's my list of aggregation operations. I'm renaming this column as my count in the solution. So in an SQL query, it would look like select my count as count property number from property for rent where the rent is greater than 350. Okay? And then if you want to add grouping operations, you put those before the tau, and you list the attributes that you are grouping on. So the primary one first, then any secondary ones. So here we're finding the staff who work in each branch, the number of staff and their combined salaries. So we are ordering by branch number because we want to find the number of staff in each branch and their total salaries. And so we're counting the number of staff and the sum of the salaries, and we're renaming the results my count, my sum, and then branch number can appear as well because it's one of the grouping attributes. Okay, so when you do the homework, just look up my slides or look it up in the book. Do I remember what these meaningless Greek letters are? Nope. I remember the one for selection and the one for projection because I use them so much, and I remember the bow tie for joins, but these grouping operations are ridiculous in my opinion. Okay? Okay, so let's just back up for a moment, and I'm going to go all the way back to the joins. There we go. So here's an equijoin in the relational algebra. And the reason it's called a procedural language is because it's kind of specifically saying what is the order of operations. So it's saying, by the way it's grouping these things, it's saying first project out ID and name from student. And over here, project out course ID and comment from courses. So do those operations first. Then do a join using this operation here. So the relational algebra is specifying the order in which the operations are performed. And it's specifying the operations. So it's still somewhat procedural. Okay, that works for those of us who are programmers. It doesn't work as well for non-programmers. So what they really wanted with the relational databases was a declarative, non-procedural way of specifying queries, and they hit on something called the relational calculus. Don't let this fancy name intimidate you. This isn't even as hard as probably what you saw in 311. So, in fact, SQL is very much based on the relational calculus, and most of you have no problems formulating SQL queries. And as you'll see, I recommend that generally the way you compose a relational calculus query is first compose the corresponding SQL query and then map the SQL query into a relational calculus query, because it's a lot easier that way. But before we get to all that, let's just get through the formalisms that we need to talk about. Okay, so again, with the relational calculus, the query specifies what we want retrieved, but not how to retrieve it, whereas the relational algebra also specifies how to retrieve it by saying first do the projections, then do the join. And what you're doing in the relational calculus is you're specifying a predicate. And that's just a truth-valued function into which you substitute arguments. If that sounds complicated to you, all that is the where clause. The where clause is a predicate. Okay? That's all it is. So what they're really saying with the relational calculus is when you specify a predicate, that's really just the where clause. Okay? So you're specifying a predicate, and what you're going to do is you're going to substitute values in for the variables in that predicate. So for example, you say where salary is greater than 10,000. So all you're doing is iterating over all the tuples, in this case in the staff relation, and for each tuple you substitute in the value for salary, and the so-called proposition that results is either true or false. And if the proposition is true, then you include the tuple in the result. So you start with a predicate, and then when you substitute in specific arguments, it is called a proposition, and it's either true or false. Okay? So these are just mathematical terms that mathematicians throw around for things that actually you probably intuitively understand, but they like to talk about things formally. So then they want to talk about the different ways that you form these predicates. And the basic thing is the predicates contain variables. Okay? So there's two types of variables. There are things called tuple variables, and these are variables that range over each tuple in the relation. And they correspond to what you see in the from part of an SQL query. So when you say select, let's do a pen again. So when you say something like select, I'm going to say star from staff, okay, and then I'm going to say where salary is greater than 10,000. Staff is a tuple variable, okay? So basically, X is a member of staff. So I could have said select X from staff X. So X would be my variable, and the range for X is all the tuples in staff. So then for each tuple in X, we're going to substitute in the values for that tuple, which is the salary field, and determine whether that predicate is true or false. Okay? So I just went over tuple variables, and the way you say that in the relational calculus is you give the name of the relation, and then you give the name of the tuple variable. That's just like saying select star from staff S, right, in SQL. This really maps directly from SQL. And then to find the set of all tuples that some predicate matches, you write it like this in the relational calculus. So it's the set of tuples in S such that when you apply the predicate to that tuple, the proposition is true. Okay, so here's a couple of examples. So we want to find all staff making more than 10,000. So we say it is the set of tuples in S such that S ranges over the tuples in staff and S dot salary is greater than 10,000. And that would return all the columns in the relation. If all we're concerned about is a subset of the columns, then we specify those columns using a comma-separated list on the left side of this bar. So here, if we only care about is salaries, we'd say the set S dot salary. Okay? Now, how does this map to an SQL query? Let's just take again a quick look. If I was doing this as a query, it would be select S dot salary from staff S where S dot salary, if I could spell, is greater than 10,000. So all we're doing, in effect, up here is we're taking the from statement and the where statement and we're putting them together using an and clause. And everything that appears in the select list goes to the left of the vertical bar. Everything that goes in the from statement and the where statement goes on the right side. Okay? Are we good so far? Kind of see what's going on? Okay. So this is saying what I just told you, which is if you're having trouble writing a relational calculus query, write the SQL query and translate it. And the translation, again, is everything in the select clause goes on the left side, and then everything in the from clause is a tuple variable. So you simply replace in the relational query for each relation, you'll name it, give it a tuple variable name, and then you'll put and signs, and that's what this vertical caret is. And then you take the where clause, see, where is appended to the tuple variables with an and. So you just take the where clause and you append it to the tuple variables with an and. This is a very important slide, slide 47, for your homework assignment number 3. Okay, you might want to write down slide 47 because this will help you with homework number 3. Slide 47. Now, we start to get a little more complicated. The relational calculus introduces a couple quantifiers, there exists and for all. And when you have a tuple variable that is qualified by, so let's just show an example. So there exists means if there is any tuple in the relation that satisfies the predicate, then the proposition is true. So any tuple, it could be false for every single tuple but one, as long as you find one tuple in the relation that satisfies the predicate, then the proposition is true. So here we are printing all staff who work at a London branch. So we're letting S range over the tuples in staff, and for each staff member we're asking, does there exist a branch such that the tuple lies in the branch relation and the branch's city is London and the staff's branch number equals that branch number. As long as there is a single tuple in the branch relation that satisfies this predicate, that staff member will be included in the result. Okay, so there exists is like one big or statement. As long as any one of the propositions is true, then the whole proposition is true. Okay, for all is the opposite. It's like a big and. It means that the proposition is true only if the predicate is true for every single tuple in the relation. So it's the opposite. There exists is very lenient. For all is incredibly strict. It has to be true for every tuple or else the proposition is false. So here we're saying for all B is in branch and B dot city is not equal to Paris. So we're saying that this predicate is true only if there is no branch in Paris. If even one branch is in Paris, this predicate is false. Okay? And as you can see, when we use a there exists, we always include tuple variables. For there exists or for all, there's always one or more tuple variables associated with them. And these are called bound variables. So variables associated. Okay, so variables associated with there exists or for all are called bound variables. And their attributes cannot appear on the left-hand side of the set. So their attributes do not appear in the solution. Okay? Whereas those that appear outside of a quantifier, like staff S, these are free variables. So if they're outside, okay, that is a free variable because it appears outside of the quantifiers. And any attribute in a free tuple variable is free to show up in the result. So here we have attributes from S, but you don't see any attributes from B in the solution because B is a bound variable. Okay, so that's all that this slide is saying, is that tuple variables qualified by for all or there exists are called bound variables. Otherwise, they're called free variables. Only variables to the left of the bar may be free variables. Okay? And if you don't exactly recognize what this actually is a semijoin. Okay, I could write this as, let's see, I could say staff, whoops, but I need the pen. So I can write this as staff joined, actually not join, I want the semi. Is this going to give me an eraser? See if I get an eraser. No eraser. Wow, you have to be perfect. Okay, not a semi-join. So this is a little arrow, staff with branch, and then what we care about in the branch, okay, I'm going to have to head over here. Come on. I need to be able to erase. So what I was doing was staff joined, semijoined. Staff semijoined with a branch where the branch dot city is London. And I was projecting out, what was I projecting out? Staff dot first name and staff dot last name. So over here, staff dot first name and s dot last name. So all I was doing there was a semijoin. That relational calculus query was a semijoin. In the homework assignment, you are also asked sometimes to give the equivalent relational algebra expression for a relational calculus query or vice versa. So if you are asked to give the equivalent relational algebra query for that relational calculus query, you're seeing it right there. Okay? That is a semijoin. Okay. And as you probably learned very early on with De Morgan's laws, you can interchange for all and there exists by simply for all is the same as saying there does not exist, and then negating whatever the formula was or the predicate was for the for all. So when I say for all B dot city is not Paris, that's the same as saying there does not exist a B such that B dot city equals Paris. So whichever way you're comfortable with saying it, you can either say for all, or you can say there does not exist and then negate the predicate for the for all. Okay. So now we come to how do we express our predicates, which are called formula. So a well-formed formula is one made out of atoms. So an atom is either a tuple variable. So this says SI is a tuple variable that ranges over R, so that's an atom. Or it is a simple relational or Boolean predicate. So here we are comparing the attributes of two different tuple variables using either a relational or Boolean operator, and here we're comparing it with a constant. So the forget which this, I always forget my Greek letters. At any rate, this is an operator. And then we can recursively build up the formula. Any atom is a formula. So is their disjunction. So doing F1 and F2, F1 or F2, or the negation. So you can see we use the arrows or carets, whichever way you prefer to think of them, and the not operator is what is it, apostrophe, not apostrophe. Oh, shoot, tilde. It's a tilde. And then if you have a formula with a free variable x, you can turn it into a existential formula with x as a bound variable by saying either there exists xf or for all xf. So pretty simple. Those are the formula in the relational calculus. Okay. So to give you an idea of how these operators are used in SQL or in the relational algebra, when you're doing the Boolean operators, those are typically used with select queries. When you're using there exist, that is often being used for a semijoin. And when you say not there exists or for all, you're typically doing an integrity constraint. So as an example, you might be saying all staff members must make less than 100,000, or comparably, you could say there does not exist a staff member who makes more than 100,000. For the second example, there does not exist a staff member who manages more than 100 properties. Or equivalently, for all staff members, for all staff members, the number of properties managed is what? What's the comparable for all for the second one? Less than. So for all staff members, the number of properties managed is less than 100. Okay, whatever floats your boat. If you feel more comfortable with exists, you use it. If you feel more comfortable with for all, you use it. If you're trying to translate this from SQL, you'll use there exists, because I don't believe for all exists. Okay, now remember that the relational algebra had union, intersect, and set difference. So here is the comparable queries, and I apologize for it being kind of small print here. I'm going to do the two that are more understandable first. So to get set difference, it's the set of tuples in B such that there does not exist a tuple in P. So here we're trying to find all cities in B that are not in P. So it's any B such that there does not exist a property P where B dot city equals P dot city. Makes a fair amount of sense, I think. It's almost exactly the definition of set difference. Similarly, for intersection, if we're trying to find all cities that are both in B and P, we are trying to find a property where the property city equals the branch's city. So basically, if there exists even one property such that that tuple is in P and its city is equal to the branch city, then we include that city in the result. So I think intersection is pretty self-explanatory in the calculus. The union is not, and I'll admit I still try to get my head around this one. So if you take the union of the cities that are either in a branch or in a property for rent, what you're saying is either there exists a city in the branch relation such that B dot city equals T dot city, or there exists a property in the property for rent relation where P dot city equals T dot city. What I find so hard to understand about this is nowhere do you see a definition of T as a tuple variable. That's why I have trouble wrapping my head around this. The reason you don't see T as a tuple variable is because there is no relation that you can have T range over. It can't range over just the branch relation, and it can't range over just the property relation. Okay? In some sense, it has to range over both, but there's no way of saying that. So you just end up having no mention of T as a tuple variable on the right-hand side. And I admit I just have trouble wrapping my head around that, but it is what it is. For me, I just memorize it. I can't even really give you an intuitive description because that's the one that I've not yet really been able to wrap my head completely around. Good news, it's not in the homework assignments, and I don't expect you to be able to. It might show up in the quiz. I don't believe it does. So there you have it. Questions about the set operations? Okay. And here comes set division. And actually, set division isn't that brutal in the calculus. It's actually fairly easy. So what I want is, let's say I'm a tourism official here in Tennessee, and I want to send out a flyer to all tourists who have visited every state park in Tennessee. Okay? So I have three relations, a tourist relation where it gives the tourist name and the address of the tourist, because obviously I want their address for the flyer. And then I have a visit relation. So for every visit to any park in the country, I have the name of the park and the name of the tourist who visited the park. And then for all parks, I have the park name and the state in which the park is located. So now I want all tourists who have visited all parks in Tennessee. So the way I say that is T is my free variable. It ranges over the tourists. And for all parks, P is going to range over park, and we have one of two things. Either the state of the park is not equal to Tennessee, i.e., any park not in Tennessee I don't care about. So if the park is not in Tennessee, then the predicate is true. So if the tourist visited a park in Wyoming, the proposition is true because the state is not Tennessee. Okay? Or for that park, so if the park is in the state of Tennessee, then there must exist a visit such that the name of the tourist matches the visitor name to that park. Okay, so the tourist name equals the tourist name in the visit, and the park name in the visit equals this park name. So you'll notice we're actually using two bound variables, P and V here. But I think that makes a fair amount of sense what's going on. Okay, so for every park, either the park is not in the state of Tennessee or the park is in Tennessee, and there must exist a tuple in the visit relation such that the tourist has visited that park. So in fact, set division is fairly succinct in the relational calculus. Questions? Okay. So again, I think a lot of times it's just easy to go with examples. So here's an example where we're listing the names of all managers who earn more than 25,000 pounds. So you can see this is a single relation query, and we're using s dot position equal manager and s dot salary greater than 25,000. So that's pretty simple. Now we'll do a join, and this is a semijoin. You can tell that because there's two relations involved, S and P, but only S appears on the left-hand side, so it's a semijoin. And we're trying to find the staff who manage properties for rent in Glasgow. So we're interested in any staff member, S, for whom there exists a property where the property city is Glasgow, and the staff member managing that property, P dot staff number, is equal to S dot staff number. And here is the literal translation of that query to an SQL query. So this is a subquery. Remember, does anyone remember what exists is used with? What type of subquery that is? You had scalar, row, and table were the three types of subqueries. Row, very good. So exists is used with row subqueries. In is used with table subqueries. So this is actually a row subquery. So the relational calculus uses a lot of subqueries. Anything that involves a there exists or a for all is a subquery. Okay, so in this case, we're selecting all staff from staff S where there exists, and we're selecting from property for rent any property that is managed by that staff member that is in the city of Glasgow. That's a literal translation of this calculus to the SQL. Translates pretty directly. And guess what? You're also asked to do this on the homework assignment for number 3. Translate relational calculus queries to SQL queries. Okay, and here is one that will trip you up. Okay, so here was list the staff who manage properties for rent in Glasgow. This is the right way to write it. This is the wrong way. So I'm going to make sure that you understand by putting in big red letters. Whoops. Oh, come on. Wrong. Okay, this is wrong way to do it. So you could be tempted to say, okay, I'm going to write it just like I would write a join in SQL. So you would say, select S from staff, natural join, property for rent. So S and property for rent would be the two tuple variables from your from statement, and P dot staff number is equal to S dot staff number, and P dot city equals Glasgow. This looks just like the join, well, it doesn't look just like the join syntax from SQL, but this is essentially what a join looks like in the SQL language. Okay, it could be translated, seemingly, this could be translated. I'm now going to come out of here. Okay, seemingly this could be translated as select S dot star from staff S, natural join, or just actually do the straight out from staff S, property for rent P, where P dot city equals Glasgow, and P dot staff number equals S dot staff number. So this is the kind of comparable query. This is a valid SQL query, but this is an invalid relational calculus query. You might think, why? The reason is that every free variable, and here P is a free variable, must have attributes on the left side of the solution. It's just a rule. And P does not appear on the left-hand side, therefore this is an invalid relational calculus query. So any variable that is a free variable in a relational calculus query must appear on the left-hand side. And if it doesn't, then it must be a bound variable. Therefore, this query is wrong, even though the comparable query in SQL is this one. Okay? So this is a semijoin. And the only way you can write a semijoin in the relational calculus is the previous way. So if we go back, you have to write a semijoin using a subquery. You can't write a semijoin without using a subquery. Okay? And you might be tempted to say, okay, this is a valid query now. So this is the same query, except now, in addition to selecting the staff name, I'm also asking for all the details of the properties managed by that staff. Now this is legitimate, because now both P and S appear on the left-hand side. This is fine, but the issue is that I'm also showing all properties that the staff is managing. In the previous one, I was only showing staff who managed a property in Glasgow. So even though this is a valid query, it's not the same as the previous one. Okay, so if you are including in the result attributes from both sides of a join, then you can write it in a straightforward manner in the relational calculus. Then it looks just like the join syntax in SQL. It's only semi-joins where you run into issues. Okay? Okay, so here's one. We're listing the names of staff who currently do not manage any properties. So this is, again, would be done with a semi-join of some kind. It looks like a semi-join. So we're looking for any staff member such that there does not exist a property that is managed by that staff member. So there does not exist. Or comparably, I could have said, and for all properties, the staff number for that property is not equal to our staff number. Either way works. We good? I know you're kind of quiet, and I'm crunching through examples. So if you have any questions, holler. Okay, so now this is, again, what would be an easy join in SQL, but because all we care about is the client's names who have viewed a property for rent in Glasgow, it becomes a semi-join. And therefore, we have to use this subquery syntax. So we want any client for which there is a tuple in the viewing relation and a tuple in the property relation, such that the client number is in that view. The viewing tuple has the same client number as our client, and the property number associated with that tuple has a entry in the property relation where the city is Glasgow. Okay? So you could write this, the corresponding, if I asked you, do we have the, nope, we don't. So I could ask you to write the corresponding SQL query, and if I did, the corresponding SQL query would be select, let's do it in a different color. Let's do it in green. So it would be select c.fname, c.lastname from client C. Now we'll do the from on a separate line. From client C, natural join, viewing V, natural join, property for rent P, and P.city equals Glasgow. And I know this is kind of small, so I'll try to, for a moment I'll do that. I'll bring it up. I'll make this bigger. And I'll put that up on the big screen. So that's the comparable query. Select c.name, c.lastname from client C, natural join viewing, natural join property for rent, and P.city equals Glasgow. Pardon? Oh, I'm missing a where. Thank you. It's not and, it's where. Very good. Thank you. Where. Where P.city equals Glasgow, and I need a semicolon too. So that's the comparable relational calculus query. Not, sorry, comparable SQL query. Okay? And just a few last things. You can't say something like that in the relational calculus because you're saying the set S such that S is not in staff. That would lead to an infinite set of possibilities. So we add the restriction that all values in the result have to be values in the domain of the expression. So in fact, this is the empty set because there is no staff member that is not part of staff. If they were part of staff, they would be in it. So you can't write nonsense like this. Okay, so very quickly, because just want a quick, going back to slide 47. When you're asked in the homework to formulate a relational calculus query, my recommendation is that you generally, unless it's simple, that you first try to write the SQL query, and then you map that SQL query into a relational calculus query. And again, the attributes you select go on the left-hand side of the bar. Then every tuple becomes either a free variable or a bound variable. How would I know whether it's a free tuple variable or a bound tuple variable? Very good. If the relation's attributes show up in the select clause, it is a free variable. If they do not show up in the select statement, it is a bound variable. If it is a bound variable, what can be said about the clause in which that tuple variable will appear? What will precede it? Very good. It will be preceded by either a there exists or a for all. So if it is a bound, so in your SQL query, if it's a tuple variable and it does not show up in the selection list, it's going to be a bound variable in your relational calculus query, and it will need to be qualified by either a there exists or a for all quantifier, okay? And then the where clause, so the tuple variables appear on the right-hand side, and the where clause is simply appended with an and statement, okay? The other thing I want you to remember, if it's a semijoin, then you're going, like this is a semijoin, you're going to have to use a subquery. So there exists and for all are like subqueries. Okay, and basically they're like row subqueries. And you're going to have to, for a semijoin, you're going to have to use a there exists. For a normal join where attributes from both the left and right side relations appear in the result, such as this one right here, then it's okay to write it out as you normally would in SQL. But for a semi-join, it's not going to look quite SQL-like because the right side relation is going to have to be a quantified tuple or quantified variable, and it's going to show up in a there exists clause. Okay? Okay, so remember, there's no class either Tuesday or Thursday of next week, but you are responsible for the lectures, and I will have them posted by tomorrow. And you are also responsible for the quizzes that go along with those two lectures. And I will see you a week from Tuesday. So have a good week and a half.